Good morning everyone, I'm here today to talk to you about electronic structure and the chemical bonding of the ternary component Ce2, germanium, selenium under pressure. My work plan is given as follows. Firstly, we will start by introduction. Next, we will look at the calculation method. Then we will talk at our result and discussion about chemical and electronic property. Finally, we will finish our representation by conclusion. The major goals of the solid chemists have been to achieve a comprehensive understanding of the interrelation among stoichiometry, crystal structure, physical property, and the chemical structure of the solid-state compound. Based on fundamental understanding of this relationship, we can create a semiconductor material which are precisely designed the structure with properties specifically tuned for certain purposes. Multinary semiconducting components continue to attract a great deal of attention, mainly due to their electronic, chemical, magnetic, and optical properties, and their wide range of technological application already implemented, in addition to a myriad of potential applications currently being explored. The numerous possibility for chemical substitution and stoichiometries in the ternary, quaternary, and the more complex multinary composition provide a great versatility for obtaining the fundamental material property, a paradigm of material engineering for a given desired and application. The ternary component Ce2, Ge, SU3 belong to the quaternary diamond-like semiconductors with a universal composition, where the first element located in the column 1 in periodic table is the copper, and the second element in the four column of periodic table is the germanium, and the third element in the 5 column periodic table is the Su S or T. This is one of the two probable groups of the threefold normal derivative of the binary component ATB4. These components have fascinating semiconducting properties, and because of the low band gap, these materials are widely applied in the photovoltaic devices in the near-infrared region. This type of the component have low melting points, which can be reduced with the addition of the atomic number of anions. Performed first principle calculation to investigate electronic and chemical property of this component under pressure based on the generalized gradient approximation developed by the PPO-Sol chain within a density functional theory DFT using ultrasonic pseudo-potential. The cutoff energy of the plane wave is set at 440 electron volt for all property, and the Briançon integration using Moncaris-Bay chain is to be 212 mesh for all optimizing geometry structure and calculated electronic property. The unity cell of this component determined in the study contains 6 order crystallographically independent 2 copper, 1 germanium, and 3 selenium. Also, as can be seen in this figure, the selenium atoms of the structure can be tetrahedrally coordinated by the quotient 1 selenium by 1 copper, and 2 germanium, 1 selenium by 1 copper, 2 copper, and 1 germanium, and 1 selenium by 2 copper, 1 copper, and 1 germanium, as can be seen in figure 1. In turn, all the quotients are also tetrahedrally coordinated to the selenium atoms. The electronic property of this component, an investigation into the electronic band structure would be useful. Therefore, the result on the electronic behavior of this component under hydrostatic pressure at 0 gigapascal, 10 gigapascal, and 20 gigapascal have been shown in the term of energy band and total partial density of state. The calculated band structure of this component along a high symmetry point of the first superunion zone at ambient pressure is plotted in figure 1. As shown in this figure, the band structure of this component is more complex and carries more structure. Hence, the band structure confirms the direct energy gap between the top of the valence band and the bottom of the conduction band at G point. This is the regular performance related to the increases of the lattice performance. The electronic structure specifies that this component is a semiconductor with a direct band gap at about 0.05 electron volt. When the applied pressure changed from 0 to 20 gigapascal, the energy bands became more dispersive and the hybridization among a state of copper and the sp state of germanium and the sp state of selenium increases both in the conduction band and the valence band, leads to a strongly mixed character. On the other hand, the band dispersion centered at the G point are invariable, but are broadened at the full band structure. In the meanwhile, the conduction band and the valence band are still overlapping and crossing the Fermi surface, suggesting that this component have a metallic behavior under pressure. The calculus density of the state at the pressure of this component are shown in figure 3. From this figure, we can see that the partial density of states for this component under pressure is similar to zero pressure, with a minor difference in detail, which may be caused by the change of the crystal structure induced by the pressure. Also, as can be seen in this figure, that the state of the copper is separated in two parts. The main part is located from the minus 7.4 to 0 electron volt, and a small part is from 110 to minus 7.5 electron volt. Comparing with the p state of the selenium, we may realize that the separation of the d state of the copper is due to the covalent bonding between the d state copper and the p state selenium. The d state copper located from the minus 7.4 to their electron volt is corresponding to the PD anti-bending state, while the D state of the copper from the minus 10 to the minus 7.5 is corresponding to the PD bending state. The overlapping between the D state copper and the P state selenium is rather slight, indicating a weak covalent PD bending. The calculated total density of the state from this component is presented in figure 3. As shown in this figure, the total density from 110 to 4 electron volt is mainly composed by the D state of the copper, the P state of the selenium, and the sp state of the germanium. The valence band close to the Fermi level is mainly made up of the state D of the copper and the P state of the selenium, and the conduction band is mainly formed from the state S of the germanium and the state P of the selenium. To gain more insights in the nature of the bending characteristic, the electron charge density distribution of this component under pressure along 110 plane have been calculated and displayed in figure 4. As can be seen in this figure, the highest charge density is found to be on the copper ions. Consequently, with a projection of the partial density of states shown in figure 3, the interaction charge density indicates the strength of the covalent bending, as may be seen from this figure that the covalent bending between copper and selenium is rather weak, whereas the bending between selenium and germanium is a little bit stronger. We will show that the weak covalent between the copper and the selenium bending is important to understanding of the low lattice thermal conductivity in this component. Meanwhile, under pressure, it is seen, as can be seen from this figure, that the electron density of the copper, germanium, and selenium atoms show a more significant overlap than those under zero pressure, which indicates that the pressure has a great impact on these atoms. Besides, we summarize the atomic milligram population and the band length in table 1. As can be seen from this table, the different bending characters take place in the atomic interaction of the considered system. The copper selenium and the germanium selenium are equivalent bending. We may observe also that the bending population of the germanium selenium band is clearly much larger than that of the copper selenium. The medical charges are determined to be 0.31 for copper and 0.77 for the germanium atoms and minus 0.18 for selenium atoms. We can see that the electron run from the copper to germanium and selenium with gaining a total energy at about 0.31 electron per atom. The values of the medical charge is representative of the concurrent small ionic and equivalent bending in this component. When applied pressure, the band length and the charge molecule is increases. Finally, we summarize our result as follows. The electron properties have been studied for the calculation of the band structure, density of the states, and the charge densities. It shows that these crystals belong to be semiconductor with a pseudo gap at about 0.05 electron volt at low pressure and has a metallic behavior under pressure. Moreover, the analysis of the charge density distribution with partial density of the states indicates that this component is a ionic covalent component. A million charge population analysis show that the charge transfer during the geometry optimization and the presence of the concurrent ionic and covalent bending in this structure. Moreover, the analysis of the band length population show that the copper selenium band possesses the stronger covalent bending strength than germanium selenium bands. And thank you for your listening.